In this video we talk about phased plots. Phased plots for autonomous differential equations of this form, y prime equals f of y. So this is an autonomous differential equation. Let me remind you a little bit of what we did earlier. We looked at differential equations of the form y prime equals f of t, right, where y is the dependent variable and t is the independent variable. And we saw that these equations, first of all, are called pure time differential equation, and this can actually be solved by using the antiderivative of f. And this makes it a rather easy and powerful method. Now these autonomous differential equations down here, they cannot be solved by the antiderivative. So we need something else. And this something else is, of course, the phase plot. So in this video I will tell you everything about phase plot. It is a very powerful method. We need a minimal amount of mathematics and are still able to really understand an autonomous differential equation. So let's gear up and get started. So what we really only need to know is what the derivative means, the derivative of a function. Right? So for example, if y prime is positive, then what? Well, y is increasing, right? We all know this. So then y of t is increasing. Now if y prime is less than 0, then y of t is decreasing. And if y prime of t is equal to 0, then what? Y of t doesn't change, so it is constant. Now let's look at the differential equation given here below, y prime equals f of y. So you see that y prime is actually given by f. So whenever f is positive, this means y prime is positive, which means the function is increasing. This is so cool. So the sign of y prime of t is given by f of y. Okay, so meaning if f of y is positive, then y of t increases. If f of y is negative, then y of t decreases. And of course, if f of y is equal 0, then y of t doesn't change, so is constant. This is so cool. So let's use this in mathematics. Let's do a phase plot. So I draw a coordinate system where I plot y, and I'm looking at the differential equation y primes equals f of y. And now I just plot the function f, because I would like to know where is it positive and where is it negative, etc. So let's just plot an arbitrary function f, so maybe something like this, f and y. According to what I just described, I just need to look at the sign of f, where is f positive and where is f negative. So let's look at this region first. Here f is clearly positive. This means the solution would increase, y of t would increase. But where is y in this picture? Well, y in this picture is here. It is on the y-axis. So whenever f is positive, y is increasing, and I indicate this by arrows going to the right. Okay, let's look at the next bit. So here f is negative. So then y is decreasing, and I add arrows pointing to the left. And so on. So in the next bit, f is positive, y is increasing. Here on the left, f is negative, y is decreasing, and here it's increasing again. Now equilibrium points are points where y does not change, meaning f is equal to 0. So the equilibrium points can be very easily seen as points where the function f crosses the y-axis. So it is here, and here, and here, and here, and here. So isn't that cool? And so I know exactly what the differential equation does. When I start, for example, here, I know that I'm driven up and driven up and driven up until I reach this point, and I don't see to go across the point, because if I go right of it, then I'm driven back down. So this is called a phase plot. So let's do 3 real examples right here. The first one is the logistic equation, a very famous equation in differential equations. It is y prime equals y times 1 minus y. And now here the function is plotted. We see the function is positive. So the solution would be increasing here, decreasing here, decreasing here. The next one is called an Allais effect. So we will study the biological meanings in class, but not in this video. But here again, f is positive, arrows to the right, here arrow to the left, arrows to the left, arrow to the right. So this is super straightforward. And then here a more complicated example, you can do the same thing. Increasing, decreasing, increasing, decreasing, increasing, decreasing, etc., etc. So, what does this mean? How can we understand what we just did in the phase plot? To help you understand this, we draw actually two graphs. On the left here, I draw the function f of y as a function of y. So this is the right-hand side of the differential equation, shown up here. And in the specific case, we have the logistic model y prime equals y times 1 minus y. On the right-hand side, however, I plot y as a function of t. You know, y of t really is the solution we are looking for. And we are interested how this behaves as a function of time. So you notice that between left and right, the x-axis is quite different. On the left it is y, on the right it is t. Now let's pick as an example 3 initial conditions, and then let's see how the solutions look like in the phase plot and how the solution look like as time-dependent solution. Let's pick 0.2 in red, which is here. That would be an initial condition for y of t. Or 0.2 is also here in our phase plot. So this could be our case number 1, and let's call this case number 1. Or I look at 1.2, we could also start above the blue line, which I call case number 2. And then 1.2 is sitting right here, which is also case number 2. Okay, and then let's do one more. So maybe gray down here at minus 0.2. Let's call this case number 3. So that would be here. And this is case number 3. So first of all, in the phase plot of f, there are 2 special points, which is this 0 point here and the 1 here. And at those points, f is equal to 0. But if f is equal to 0, look up here, then y prime is equal to 0, which means y doesn't change. So whenever I start at 0, then y prime is 0, y doesn't change, so y will stay 0 all the time. So actually this axis should become blue, as good as I can do it. Same story here, if I start at 1, then I will not change. F is 0, so y is constant equal to 1 all the way. That's why I had the blue line here in the first place. Now let's look at the initial condition number 1. So here in this graph, I start at 0.2 and I evaluate my function f. And of course f here is positive, which means I have a positive slope. So I have a positive slope here. In the phase plot, it of course means my function is increasing. I have arrows going to the right. So then the function increases, I get maybe close to 0.4, so which is somewhere here. And then the f value is increasing. The f value is the slope of the curve on the right. It is increasing there, so I get a little bit steeper slope somewhere here. But I'm still increasing. I follow these arrows in the phase plot. So then I get maybe to 0.8 at some point, and the slope is maybe a little bit flatter. And then if I go further and further along the curve of f, I come closer and closer to 1, but the slope gets flatter and flatter. So what this looks like is like this. I asymptote to 1. So this is now the solution. Let's call this y1 of t for the first case. So let's practice this once more with the second solution. So in 2 I start at 1.2, which is here and here. In the phase plot I have an arrow going to the left. If I evaluate the slope, which is the function f, I am steeply negative. So from here I go down. I have a negative slope. But then going down and down, the slope stays negative, f is negative, but I get closer and closer to 1. So what happens is very similar to the other case. I asymptote to 1, I'm still decreasing, but the slope gets less and less. So this would be a solution y2 of t, starting at the point 1.2. And so then we do one more case. If I look at case 3 and starting at minus 0.2, so here the function f is negative, so I'm decreasing. And then again, starting at this point, I evaluate f here, which is negative, so I have a negative slope coming out of here. I'm driving to the left. Now I'm leaving my picture, but you can easily imagine the further I go left, the further negative it gets. So this falls down actually rather quickly. So that would be y3 of t. So there's a direct relation between the phase plot on the left and the structure of the solutions on the right. If you think this was a little bit quick, please print out the PDF file of this video and do it yourselves. Let me summarize. So to analyze an autonomous differential equation y prime equals f of y, we first plot the function f. And then we know whenever f is positive, the solution increases. Whenever f is negative, the solution decreases. Whenever f is 0, we have an equilibrium point. Now, tell me that this method is not cool. I don't believe you. Excuse me? Excuse me? Dr. Hillen, excuse me. Oh, hey, Tolo. You're painting again. So what is it this time? Beautiful.